Alrighty, no problem. I'll run it from my side. So the zkVM space is really new, but it's also very confusing. And so we are looking to be the leaders in helping to define mental models for layer two scalability, for zkVMs, and for zero knowledge proofs generally, because we have some of the most brilliant minds in the space working on it today. So that's what I do. But today I'm going to be wearing another hat, which is discussing what zkSync is. So zkSync is a layer two rollup powered by a zkVM. And if you're new to the space, you might be like, what's that mean? I think a lot of the LearnWeb3 DAO folks, it's a little less, a little more familiar, but just in case, we're going to go into it as well. So what is layer two? Layer two is a blockchain network built on top of another blockchain, typically Ethereum in this case, which is meant to improve scalability by moving execution off chain while maintaining the same security guarantees. So this is critical, and there's a lot of distinctions that we can make within this description. The main thing is understanding that layer twos are addressing the scalability issue of sort of state bloat and slow network activity on layer ones by separating out things that don't work very well on layer ones, which is execution. What I mean by that, if anyone has ever synced a layer one execution client, you know that it's extremely, extremely slow. It takes up a ton of RAM. The reason why is that it's doing all this incredible execution read-write operations on your disk to encode in a Merkle tree and processing a lot of transactions, and it's extremely, extremely slow. You know, I've broken multiple computers trying to sync Geth or Besu, and so we know that execution is very challenging on the layer one layer. However, it's extremely bulletproof. Like no one has hacked layer one, no one's hacked Ethereum. It's extremely, extremely reliable as a security-based layer. So the idea here is that we're seeing Ethereum as this a little bit slower moving, but much more secure settlement layer. And the things that it cannot do well, which is execution, we're moving off into other networks called layer twos. Now, the reasons they're called layer twos and not side chains or things like that is that they create these checkpoints back on layer one. And we're going to dive into this a little bit here. But essentially, a layer two will typically deploy a contract to layer one that creates a certain state checkpoint. So essentially, a layer two contract deployed on layer one is a Merkle tree. So if you imagine the Ethereum state as a Merkle tree as it exists on your computer, we're essentially replicating that in a smaller contract. And at a certain checkpoint, layer twos will send updates to that Merkle tree within that contract on layer one. So I sort of imagine it in like old school games when you'd be going through a world and doing a bunch of achievements, and then you'd always save at a certain checkpoint. So you'd be able to always go back to that checkpoint. That's the same idea of layer twos, creating these checkpoints on layer one. And this is very, very critical because it makes the quote unquote inheriting the security guarantees of Ethereum, which is a big part of the layer twos. This is what sells that point, is that theoretically these checkpoints exist so that any user, if something were to happen to the L2 network, can go back and go through some sort of process and pull their funds from the layer two contract that's been deployed on layer one. Different types do this in different ways, but typically the most popular and the layer two is getting the most attention today are rollups. And rollups, as we said, sort of inherit these a bunch of executions. You can see these executions on the upper layer here, bundle them into batches. That's the process of rolling it up. And then sort of at a periodic time, they commit those to the L1 contract. They send them in the contract in a transaction to the layer one, typically using the call data, which is input data on an Etherscan transaction view. And those transactions are sent by a sequencer. So a sequencer is equivalent to a validator or a miner in a layer one network. its job is to order and then put in those transactions to layer one. And typically sequencers are run by the networks right now. Ideally, in the future, they will be decentralized, and you can run them from your computer. Like people can run them on their own and be able to submit stuff to the network itself. So here we are. We have these transactions talking about layer rollups. This is just sort of an overview of what we just talked about. There are two main flavors of rollups. One is called an optimistic rollup, which uses a very similar scheme to layer one to Ethereum, where you are, optimism is essentially just Geth that's been forked. That's why it's EVM compatible. And they are doing these, that sequencer is batching up transactions, sending them to layer one. However, they're using a fraud-proof system. So you have an ecosystem of people watching for fraud that's happening. And while the network is optimistically or like naively computing those transactions, assuming that they are good, if people catch anything bad, they can report it. And then there's a whole fraud-proof mechanism. Optimistic rollups have much longer withdrawal periods because of this security model, which is based on people watching these like fraud ecosystem. So it's much slower than another rollup technology that like a zkRollup, but it's the main one right now. The main optimistic rollups are Arbitrum and Optimism, which I'm sure you all are familiar with. They have also been in production for a good amount of time. And so on L2Beat, they're in the top of the scoreboards there. But there are other rollups. And so this is where zkSync comes in, and this is the zkRollup. So rather than using Geth to process our transactions the way that Optimism does, essentially, we have created our own EVM. So using zero-knowledge proofs, which could be its own semester of courses, but essentially, you all are familiar enough sort of broadly with zero-knowledge proofs. We're able to capture EVM data of a transaction. And rather than having to process each operation, we can create a proof which says this transaction follows the EVM rules, and we are able to change this state from state one to state two. And this is really, really huge. It requires a lot of very advanced cryptography right now, but it's really exciting. The way that I've heard it explained that I really like is that zero-knowledge proofs are to digital signatures what Ethereum is to Bitcoin. So if you think about a digital signature says the person who is holding this private key has signed this message. You don't know anything about the private key, but you do know that the owner of that private key signed the message. Zero-knowledge proofs can say much more broad statements, such as this transaction is able to communicate with this contract and do this kind of operation and make these state changes. And you're able to verify that with a single signature, a single proof, essentially. And so you can think about zero-knowledge proof. Zero-knowledge proofs is creating this much larger, expansive space, which with which you can do that sort of cryptographic certainty of processing transactions. So rather than needing to naively process transactions and just hope that someone catches the problem, which is what optimistic rollups do, zkRollups actually say, okay, we are genuinely going to create a proof that mathematically you cannot change, you cannot argue against, right? This is really huge because that kind of publicly verifiable computation is extremely, extremely powerful. And has huge implications for blockchain scalability. It's super exciting. It's being used in a number of different applications, but this is very, very cool way of translating the EVM into and scaling it essentially. I'm going to throw in a couple links here, but there's a really great article that Vitalik just did about the zk EVM endgame. And essentially, Vitalik says we want the EVM to eventually be zk compatible. That's how powerful the technology is. So right now, there are a number of groups that are working on it right now. Obviously, zkSync. We just launched zkSync Era right before ETH Denver. We've been running a version of a zk EVM now it's called zkSync Lite, which was able to mainly just do send and transfers on the EVM, which was a huge accomplishment in its own right and had been running for years. If you had done an on-chain donation with Gitcoin, that was done on zkSync Lite now. So we have been familiar with this problem space for quite some time. Our founders and the engineers who are working here are this incredible mix of OGs from the crypto space, as well as people who have come from FANG companies, major universities, from cryptographic and CS departments to work on this stuff. It's really, really compelling technology, very exciting. So we're excited to have that team. There's also Polygon has launched their zk EVM, which is similar technology. Scroll is another team that is developing an EVM equivalent. And we'll get into that in just one second, what the difference is between EVM compatibility and EVM equivalence. And then Starknet is another one that is doing a zkRollup. However, Starknet's a little bit different, where they are running their own network, Starknet, and then from there they're able to develop a system or an implementation which is used to power different networks like DYDX. So they're not actually a layer 2 in the sense that they're using Ethereum for data availability for those checkpoints that we talked about. But nonetheless, it's a very powerful system and it's a powerful team, and they're doing incredible research. So we'll let them into the club for now until we have to kick them out. So I mentioned briefly when talking about Scroll the different kinds of zk rollups. There's essentially two approaches when you are building a zk rollup that plugs into Ethereum. The first is, we want to make this exactly like the EVM. We just want to take every opcode and translate it into a circuit, a zero knowledge proof circuit, so that we can essentially just do a one-to-one. That if you have the add or subtract opcode in the EVM, you know exactly what that looks like on our zk EVM. This is the approach that Scroll is taking. We haven't been able to actually look at it, but Polygon says that's also what they're using. This is really powerful because you get, essentially it looks exactly the same in terms of developer tooling, in terms of behavior, except you get those, you get that acceleration from zero knowledge proofs. It's a little bit challenging though, because you are tied to EVM for better or for worse. So you get a lot of equivalence in terms of the source code, the bytecode, the API, gas calculations, your block root stuff, but the performance is very, very low. And so there's a way that we have been able to, so that's full equivalence, is that type 1. And then the other option is going for compatibility, saying we are going to build something that will be able to compile, and 99% of contracts will be able to be deployed onto this network with no changes. 99% of EVM contracts that are deployed on the EVM can be deployed to our network with no changes. However, it's not going to be the same. It's not going to be EVM equivalent. So there are a couple little tweaks that you have to go there, and we'll go through that as well in a second. However, you get these really, really interesting features that we can implement, as well as further down the line, because we're not tied to the EVM. We can introduce some very cool tech, such as we use a compiler called LLVM, which we can use for Yule and for Solidity, but could also be used for Rust, for example. So you could have Rust-based programs that are compiled down and can run on an EVM network or a network that has EVM checkpoints. So that's sort of the debate on crypto Twitter. and equivalence to compatibility and kind of toggling back and forth between those two. I actually think we're coming up on time pretty quickly. Oh, no, we have an hour. Okay, great. Perfect. Okay, let me give you one more slide and then I can stop to see if there are any questions. We might just power through this. Let's see here. Yeah, okay. Alrighty. Okay, so just really quick before I answer that question, Hardik. So a quick overview of where we are with layer twos. Layer two can be divided into two flavors: zero knowledge rollups or optimistic rollups. Arbitrum and optimism are in that optimistic arm. And then on this left arm, you have within zkRollups, then a kind of a spectrum in terms of equivalency versus compatibility. So we have scroll over here. That's one-to-one EVM equivalent. Polygon zk EVM, which we think is pretty close to equivalence. zkSync, which is more compatible, and then something like Starkware, which is very different in the sense that you have to have you're writing in a new language. They have a language they developed called Cairo, which you can transpile to Solidity, but it's, again, there's a lot of sort of jumps that you have to make to get from Cairo to an EVM network. So again, this is some of the educational material that we're working on. Why would you do EVM versus EVM equivalence versus compatibility? There's a number of different trade-offs. So there's advantages and disadvantages to both. There's not one to say this is the worst implementation, this is the best. All that to say, though, even though zero knowledge proofs is this blanket statement, the engineering implementation of that there are more than one ways to get to the core of the apple being sort of a zero knowledge proof circuit roll up. So originally before I came into Matter Labs, I thought there was just sort of one way to build the circuit. And the first team that built it, kind of like mapping the genome, the first team that could map the genome would be able to do it. But turns out there's a ton of different implementation issues. It's very challenging to map the zero knowledge proof technology onto EVM. And so different teams are taking different approaches. It's very fascinating, very interesting, and makes for a really rich ecosystem. Let me check this question here. Okay. So Arctic says, no, this is going to be a topic in our Web3 Wednesday tomorrow. What are your thoughts on what happened with the DApp that did an ICO or something on zkSync and funds got locked in contract because of transfer not being exactly compatible? I read somewhere that there are efforts to resolve that. Just wondering what those efforts are and what the roadmap is for that internally. Good question. Really, really great question. I will actually get to that in just 1 second. We're going to dive into our docs here a little bit, but essentially it touches on that. It touches on the EVM equivalency versus compatibility. There are some big things that you need to be aware of when building on zkSync or on any zk EVM that's not equivalent. And we have a compiler that is very, very explicit about those different issues. However, a lot of developers are moving very, very quickly. I myself am very guilty of this. And so you get a compiler error or you get a compiler warning. And I think now in the sort of the NPM age, I discard warnings just like, you might as well be, it's like junk mail in my mailbox. It's just like, forget it. Yeah, who cares? Did it compile? Great, good. I'm going to go deploy. And so that's one thing that we do want to emphasize, that because it's a zk EVM, we cannot do the kind of reorgs or we cannot change the network that even Ethereum was able to do with the DAO hack, that Gnosis Chain has been able to do with a rollback. We cannot do those kinds of rollbacks. It's literally cryptographically impossible for us to do these kinds of rollbacks, but I'll get into that a little bit more. Yeah, exactly. It's like, it's really NPM is kind of like, jaded us to warnings. But I might actually jump to, let me see here. Let me see. Let me just touch on two more things, and then we'll actually jump right to the documentation to talk about the differences, and then I can actually get into that specific case, Hardik, as well. Does that sound okay? I'm sure you all are familiar. Is that okay? Is that all right with folks? People let me know if there's any issue with that. Okay, great. So L2 beat, I'm sure you all are familiar. Some of you might be familiar with it. Let's see if it'll let me go here. Okay, great. Let's see here. Yeah, exactly. It's a challenging one. So L2 beat, this is where you can see different scaling things, but really importantly, there's this great risk analysis thing that people should take a look at. It's informing sort of the mental models that we're building right now for our courses and things. It's very, very cool. It's really important to get a sense of things. Um, but what I'm going to do, this is our quick start. If people want to start on this kind of in the background while I talk through this and they want to start building, that's great. We're sort of shifting more into the building section of the talk. Okay. So if you go to our building on zkSync, so first of all, our docs, link for our docs is right here. Yeah, totally. I know it's always very disturbing to like how easy you disregard those. It's actually a very cool project from MetaMask called Lava Moat. People are awesome, great job, super cool. People already deployed stuff. Okay. Within building on zkSync era, there is a section called differences with Ethereum. And so the main one, this was in our documentation in different ways, and we compiled it all into one page so it's easier with folks. This ICO Hardik that you mentioned had an issue with this issue, so or this part of it. So there are a few main differences once you start developing on zkSync or developing your contract or migrating your contract to zkSync. In some ways, it's very, very easy. And the tools, like we have a hard hat plugin, we have a Foundry plugin, which is coming soon. Those are plugins that we maintain as a company, so they're going to be kept up to date with the latest releases. However, even with those things, there are a couple of things you have to be aware of. The first one is that you for sending ETH on the network or sending any sort of token on the network, we want you to use call over send and transfer. So this was the issue with the ICO, is that they had used the send, and I think they used send rather than call. And so if you're, this is, when you're actually transferring funds to someone within a smart contract, there's the Solidity method, .send or .transfer, which is the go-to. These methods were actually, if you look in this, if you actually go to this link here, it talks about how send and transfer were originally developed by, I'll put this here. Yeah, right, exactly. And essentially, send and transfer have these gas limits that were meant to sort of stop reentrancy attacks. Reentrancy attacks, as is mentioned in the LearnWeb3 course, is a way in which you exploit the structuring of an interaction where there is a send transfer before the balance is updated in the smart contract for the user. The user then sends the funds to a smart contract, which has a fallback function, which produces an error. And essentially it stops, it sort of creates this sort of loop above where the function actually sort of starts deducting from the user's balance. So you're able to drain the contract of as much ETH as the contract has, because the contract doesn't realize that your balance is not being updated. So it's kind of the go-to first thing you learn about Solidity in terms of security, because it was used in the DAO hack. It was used in a lot of different attacks. There is so a lot of people, they develop these methods, but then those methods had these hard capped gas limits, which were a problem. And so essentially, it's not good policy to use send and transfer. And so now we use call, and use call with the value that you want to send. And this is a much more clear way of defining transfers. Originally, the compiler failed when you tried to use send or transfer, because you can use send and transfer with ERC20 tokens on zkSync. You just can't do it with ETH. And so in this case of the ICO, if I remember correctly, it was something about, the send was being used to transfer tokens when someone was either burning or transferring an NFT. And so that was the only way that ETH was able to get out of the contract. And because send and transfer weren't working on the network, it trapped those funds in there. So the issue originally, our compiler would fail when you were using that, but we were getting a lot of false positives of people using ERC20 send and ERC20 transfer. We couldn't distinguish with that. So we switched it from an error to a warning. So now it warned you when you compiled a contract saying, listen, if you're using send or transfer for ETH or for ETH, this will not work. Or most likely this will fail because of the gas limits on the network. But the developers did not actually test on our testnet, which is kind of critical. They only tested on BSC. And so by the time they deployed to zkSync mainnet, they discovered their problem too late. So that's the challenge. I believe there was, it was a bit of a challenge there. So, yeah. And we do have someone from our team in the chat. I believe now we were able to optimize the prover so that it was able to process send and transfers. Like, it wasn't that you couldn't use send and transfers, it's just that the call would fail because of the proving costs. But I believe they optimized the compiler so that the approver, so it was actually able to process the funds and get them out there. But I'm not sure that was, I actually don't know the status of that right now. So yeah, don't test in production. Testing in production, which is so common in crypto, would be like, if you were in Web 2, it would be, I don't even know how to describe how silly it would be. And so many people will do it. And so this is why it's a very uniquely crypto kind of issue. So anyways, that's sort of the main thing, hard to address your issue there. And then the other one is non-standard create two behavior. You don't create the same deterministic addresses necessarily with contracts, even if the same bytecode that's deployed onto Ethereum or another EVM chain. So again, we go through all these changes as well as recommendations for a way to change that. So you can look there. And I really, really, really emphasize you all to look at this and before you start doing serious development on it. It's really important. So another one is block stamp and block timestamp, block number. This is the case for a number of L2 networks. It behaves differently because you're not on L1, and so the time is different. So you want to make sure that's there. If you use any of these opcodes as variables in your contracts, you want to make sure that you accommodate for those. And then there's some deeper stuff around Yule and other sort of opcodes. So check these out. Our Discord is also available there. And then we have some recommendations as well here, mainly around gas logic, because gas logic is a little bit funny on L2s because there's always a refund mechanism of when you actually commit it to L1. Typically, you get a refund back from your fees, things like that. So that's that. And time is relative. It's true. It's true. It's all an illusion, friends. But look at that. Be sure to check that out. Another aspect is that we're going to go through developer tools really quickly, and then I'm going to go to the deployment part of the workshop. So Solidity's version as old as 0.4.12 are supported. We obviously want you to use the most recent version. We also support Viper. We have our own compilers. And most importantly, we have our hard hat plugins that we use to allow people to deploy using hard hat. And I'll walk you through that part as well. So I believe that is all in terms of that. Let me just double check, make sure I'm not missing anything from the. Yeah, I think that's all. Cool. Any questions there while I'm just setting up my environment? Have people? Yeah, so we do. So again, like I mentioned, the compiler does mark it as incorrect. Oh, okay, great. The compiler does mark it as incorrect, but it doesn't fail because it doesn't, it doesn't create an error. It's mainly a warning because, like we said, the send and transfer does work with ERC20 tokens, and there wasn't any sort of meaningful way to tease out um, what's an ERC20 transfer and what's an ETH transfer. So it did actually catch that. And unfortunately for this team, now almost everybody who's watching development closely on Ethereum knows that you don't want to do that. So, it's an expensive lesson, but we actually think that I think actually it's been handled. Alrighty. Alrighty. Question. What do you think the future for projects already launched on layer one? There are no backward compatibility between layer one and layer two once a contract has launched, right? So typically a lot of the projects launched on layer one are available on layer twos. So you can go to our ecosystem page on zkSync.io, era.zkSync.io, and see the different partners there. There's always going to be L1s have this. Ethereum still has the staying power. I think what we're going to see is applications developed specifically for layer twos, which sort of advance the Web3 ethos. So, being able to, once the sort of transaction throughput really increases and the transaction cost decreases on layer twos, I think you're going to see a lot more apps that interact with layer twos and maybe sort of can consolidate or settle to layer ones. The people using those applications on layer two might not even know that there's a crypto component to what they're doing. Whereas people who are using layer one for their applications are these hardcore folks who are very familiar with what they're doing, are doing hardcore DeFi stuff, are building these very, very niche, very technical programs that is appealing to a very specific set of audience. That'll always be there. I think they're always going to be the hardcore crypto folks, but but I think L2s are going to unlock a broader audience. So it's not necessarily what happens to the L1 stuff. It's more, what is going to be built on L2 is my question. Yeah, this is an interesting question. Do you envision a future where cross-chain gets good enough that fragmented liquidity across different L2s will not matter? Or do you see a future where very few L2s survive and there's consolidation there generally? So yeah, it's interesting. So there's always been this question about, can you, can you move between either L2s that have contracts on L1? Is there a way that you can kind of move between L2s and consolidate L2s or kind of move stuff around? And there is discussion, and this is where zk EVMs are very interesting. There is discussion around a sort of like multi-prover universe where like a prover can run proofs from different zkEVM networks the same. And so there is sort of a way that maybe zkEVMs become their own clients in the same way that we have a lot of execution clients. Maybe we have zkEVMs becoming their own clients that people can run transactions through. And so, but in terms of that sort of cross-chain things, I think you're still going to need market makers or kind of liquidity providers to do that kind of cross-chain activity. Even if there still is a layer one there, I don't think it's going to be quite the same as, it's not going to be able to, you're not going to be able to use sort of like the laws of logic to then sort of operate on those L2s seamlessly, even if they all are updating L1 fairly regularly. Okay. Okay. Will the flippings of zkRs over optimistic rollups happen soon? Playing devil advocate, what's your bull case for optimistic rollups once zkRollups are mature? So this is an interesting question. I actually think that there is a chance that optimistic rollups. So there's this great talk from Calvin Fisher from Optimism called "Rollups Don't Exist," And his argument is a separation of concerns, where it's, if you think about a roll up, in terms of like, there's sort of two parts of a roll up. The one is like the execution and sort of processing transactions on that roll up. And then there's the updating to the L1 that happens based on the side effects from that roll up behavior. Um, Technically, optimistic rollups and zk rollups look very similar in terms of the operations that they're doing within the rollups themselves. They're essentially bundling transactions, processing that execution, and then sort of like putting them into blocks, ordering them into blocks. And so I think there's a future where optimistic rollups, have to implement zk EVM, proving to the L1, because just the model of optimism, it doesn't scale non-linearly, meaning that zkVM, this is pretty heady, but zkVMs provide recursion theoretically, where you could start making zkPs of zkPs, and you start getting nonlinear scalability there. Optimism does not scale in that same way. So optimistic rollups can't scale because it's essentially, you're just sort of like running another L2 on another L2. Whereas the scalability hypothesis with zk EVMs are, once we can start doing recursive operations, then we can start bundling transactions and then bundling bundles of transactions together. And so you can kind of get this massive scalability increase there. So that's sort of a confusing answer that I hadn't thought out very well. So I hope that's not too confusing. Let me grab this stuff that I'm talking about, just because otherwise I look like a jerk. And then let me deploy this quickly to the thing. Any other questions just while I'm grabbing this? Okay. Here we go. All right, here's the Pollock talk here, and then here's this rollups aren't real. Okay. All right. Just really quickly, let me do this. Okay, I'm gonna switch here, stop presenting. And zkSync era, it's quite different because we support custom accounts that may take slightly different, typically higher number of gas and EOAs. Yeah, so this is actually will be the talk. Will be Antonio's talk next week. Will be about account abstraction and paymasters, which does not actually do higher gas cost. Well, it takes higher gas costs in the sense that it's a little bit more sophisticated operations, but apps can start paying for different developers, can start paying users gas fees. It's essentially kind of meta transactions, if you remember those, or relay transactions that are available on the network. And as a result, this is where the sort of the EOAs versus contract based accounts come into play. We still have EOAs, and our costs for those are actually quite reasonable, and definitely lower than mainnet, Ethereum, so yeah, there's actually not a gas difference in that way. Yeah, no problem at all. We keep hearing crypto adoption, but across all L1s, it feels as though we have more throughput and block space than we need at the moment. Cognitive distance of we need more smart fellows to build amazing tech versus someone just needs to win already. Yeah, I think that's an interesting. I'm sort of interested to hear people's thoughts on that, because that's a good point. And but I also think it's sort of like it's anybody's opinion there. Like yeah, what do people think about that? Does crypto actually need more tech? Does it need more throughput, or does it need someone to build a killer use case, as they say? Weigh in in the chat, as they say. Okay, so okay, so I have got okay, and I don't think I'm sure. Can people see my my screen here? Okay, cool. Yeah, people keep weighing in there. Okay, so I'm gonna clone this repo. It's not quite ready, so we haven't actually opened it up yet. But I think you're gonna be able to kind of go through this fairly easily. And if you follow the quick start, you will for sure be able to get deployed to mainnet there. So okay, first things first. Before people are able to deploy on zkSync, you need to grab some zkSync testnet ETH. Right now it's on Gurley, and I'll put this here in the chat to our bridge there to bridge Gurley funds. If you need Gurley funds, you can also grab some. I think we have a faucet, and then Paradigm also has a faucet. So you can get a faucet and then you can bridge those over. Here, I just want to talk through a couple different things. Here, we are, this is a hard hat project. You can see here we have our contracts. Our contract is this very basic greeter contract where, and I'll increase the font there, where this is the hello world that people are very familiar with. And then we have our hard hat config here. And let me also, while this is running, I'm just going to run yarn in the background just to install the dependencies. So here we have a couple of different things that we're importing. So your hard hat configuration, looks very similar. The only two things that are different is that you have this hard hat zkSync deploy, hard hat zkSync sulk. This is our custom Solidity compiler that we talked about earlier. That is kept up to date with all the way back to 0.4.x, but up to date with the latest 0.8.x. And then we have our zkSync deploy. And then there are a couple different things that are a little bit different in here. One is that you're going to have a different configuration property here, zkSulk, where we define the version of our Solidity compiler that we want. And then our default network is going to be zkSync testnet. And then we are going to have an endpoint here. This is actually, we can get another endpoint that's in the tutorial and the quick start rather. It's based on Gurley, and then we're using Solidity version 0.8.7. So let me do one thing here really quick before I see here, which is I'm going to do the env file. env. I'm not sure we'll make it here. Give me 1 second, folks. Yeah. Yeah, I am actually about to do the same thing, Hardik, and I did something very, very similar. I was supposed to set up the .env before, but I also wanted to show people how easy it was. But essentially, okay, how about this? We'll go into the hard hat here, and we're gonna have deploy your private key, and you're gonna put it in the .env here, deploy your private key. Your private key is gonna go there. With .env, you don't have to do any quotes. And then we also have our, we might not need our RPC. Oh yeah, here we go, our node URL. So this is gonna be a node URL, can be anything. An Infura one, I believe there's a couple of different public ones there. Let me grab my RPC URL here. Okay, here we go. All right. Okay, so our node URL is just this testnet.era.zksync.dev. We'll save that here. You want to put your deployer private key right here, which I won't do right now. because we're on a stream. But essentially, so if you run, now that yarn should be done here. See, look, I'm not even looking at any of this stuff. I'm just like, great, did it finish? Great, good, grand. Essentially, within the demo, if you were to just within this demo, you can just run. You could deploy it using hard hat run network girly, and then use the script girly deploy. But yes, this would deploy it to girly, and you get the contract address there. But we're actually interested in deploying to zkSync. So before I do that, I'm not going to do that. But what I can do right here is just show you what it looks like to compile using zkSync. Oh no, busted me there. Okay, let's see here. Let me see how I can get around this. All right, give me 1 second here. I'm going to play a dangerous game, and I'm just going to put a private key in here, but give me 1 second. I can't watch the chat, so I'm I think we could use it, but I am going to do this one because I don't know if it has girly ETH. Okay. I'll also make sure not to go over. Here we go. Try it one more time, even though we don't actually need it for the compiling. Okay, so really quick, you're going to see something different when you run hard hat compile using, within our hard hat config, using our zkSync Sulk plugin. One is that, typically you have artifacts and you have cache. Here you have artifacts, and within the contracts, we have our greeter, and it just looks a little bit different. The bytecode is actually going to be a little bit different. This ABI is going to be the same because the functions are the same, but this bytecode is going to be different from a bytecode that you would get if you compile just using your regular ETH compiler. That's really critical, and it's related to those differences in Ethereum that we mentioned earlier. So that's, again, something to be aware of, something to be concerned about. But then just to show, and we won't do this, well, actually, I think this one might have, we'll see if it has, we'll see if it has girly ETH. Within the quick start, we have a really great little function which allows you to deposit stuff into zk. This will automatically bridge your funds that you have on layer 1, go to layer 2. So we're going to try to do that. And then really the only thing different, we have a couple sort of estimate fees, and we have a deployer plugin that handles some of the strange sort of things, but essentially it looks very, very similar to if you were to deploy it on Ethereum. So let's try it here. If I don't have enough girly on this account, then we're just going to have to call it. And you guys can do the quick start on your own. But let's see here. Let's see how this works. In the meanwhile, I'll check the chat. Yeah, I don't know if we have L2 base cost. Yeah, I think we don't have enough unexpected error. So that is all right. We will have the quick start there ready to go. Hard hat keys. Yes, right, exactly. No, I'm good. I'm good. I think we're at the end there. And so let's see here. Any other things? Yeah, cool. So that is just sort of the simple sort of walkthrough. The only differences that you need to deploy to zkSync Era with a contract that you can already deploy on Girly. Can go through there. Follow that quick start guide, and then next week we're going to have Antonio come in and talk about some more advanced stuff. That'll be account abstraction, native account abstraction, and paymasters, which is a really, really cool UX feature that's available through zkSync native to the protocol. A little bit different from the way that Ethereum has implemented it. So yeah, please stick around or come back next week for that talk. Should be really good. Any questions? Anything else from me before we go? It's being built. It's being built right now. So you got to wait a little bit, but we will have that soon, I hope. Soon. All righty. Thanks everybody for sticking around. Really appreciate it. And yeah, come back next week. We're going to have the great Antonio come, and he's going to be great. Thank you all so much. Thank you so much to LearnWeb3. Y'all are a great community, and really appreciate it. Cheers.
Thank you, everybody, for coming. Thank you, Coogan. Appreciate you answering my questions and everything. And yeah, this was recorded, so anybody who joined late, you will be able to go on YouTube and watch it, maybe except for the first couple of minutes. But yeah, thank you, everyone. And come back next week for Account Abstraction, which is going to be very good. Very, very hyped for that.
Thanks, everyone. Cheers.
Coogan, somebody's asking for your Twitter link.
Oh yeah, it's I have a new one here just for systems, just for zero knowledge proof stuff. So check that out. It's not a lot of followers there right now, so I promise it's not a bot, but check it out. Alrighty. Thanks everybody. Awesome. Cheers.
Thank you. Cheers, guys.
Okay. Bye.